Thank you, and thank you for the honor of beginning my favorite session on black holes, jets, and disks. This is going to be a very different regime from the talks that we've heard for much of the week, especially yesterday afternoon. We know that black hole growth in the universe occurred through high luminosity, high accretion rate flows that are definitely very collisional, at least as far as the plasma is concerned. Photons is a different matter, and it's photon kinetics that I'm mostly interested here, not plasma kinetics. We're going to return to the collisionless regime later on today, but I am definitely I believe in a highly collisional regime. So you might think that that's a fairly straightforward regime to consider, but in fact, I would argue that we know very little about how these flows actually work. High luminosity accretion onto supermassive black holes. About the only thing that I'm confident of is that there's accretion power, it's thermalized into photons, and those photons are radiated. And the only reason that I'm confident about that is that if you go through this argument that probably dates from Lindenbell 1969, ages ago, that the temperature should be radially stratified, that it should be hot in the middle and cold outside. And this has been verified through heroic multi-wavelength reverberation mapping campaigns done by huge numbers of observers over many, many months. And they do indeed see that you can measure the length scale through light crossing time, that indeed the inner regions are hot and the outer regions are cold. And in fact, they can even see that the temperature is going more or less as R to the minus 3/4. And this is actually consistent with the observed optical near-infrared spectrum when you can see it as near to the 1/3. That's more or less right. But that's all that this is telling you, is that accretion power is being liberated and thermalized into photons. That it doesn't tell you that there's even a disk there. And the reason why I say that is because there are big problems, with disk models of supermassive black holes. Probably the biggest problem is that the spectral energy distribution shows a universal break at around 1,000 angstroms, suspiciously close to the Lyman edge of hydrogen at 912 angstroms, down to the soft X-rays. That is universal, independent of accretion rate, and well, high accretion rates, independent of black hole mass. And that's not what standard disk theory predicts. The reverberation mapping campaigns that I just described and microlensing show you that the optical emission radius is a little bit larger, by after 3 or so, than standard disk theory would predict. That may or may not be a big deal. But probably one of the biggest and most concerning problem is that the observed variability timescales, months, years, are way, way shorter than you would expect from the inflow time of AGN, which is hundreds, thousands of years. The very fact that human beings can observe all this variability is a big problem in AGN. And never mind the fact that if you try and put a Shakura-Sinyaev disk into an AGN, it's horribly, theoretically inconsistent. Okay, so I believe these are aspects of the ingredients that need to be included. You have to include Discmans. We observe huge outflows from AGN where m dot out is comparable to m dot in. That radically changes the radial temperature profile of the disk, likely. The stuff that I'm going to focus on here, though, are these last two aspects that AGN emit most of their radiation in the far ultraviolet. As I'm going to show you, they're heavily radiation pressure dominated. Maybe, and I'll get to the maybe later on. You're dealing with UV opacities, and that immediately introduces complexities on their own. And in fact, interesting complexities that interact with MRI turbulence if you believe that you have a rotationally supported flow. This is also an aspect likely that's going to be happening, is that there's magnetic pressure support in the flow that helps alleviate the timescale problem for variability. This has been a point of view that's been pressed by Mitch Begelman in particular, but many and his collaborators over the years. And again, it turns out that I think both are at play here. Okay, so I'm going to be just set up the stage of what the conditions are in the AGN. I very liked your talk, Mateusz, where, cosmic ray transport, you don't even know what the opacities are. Well, at least we know the opacities. So if I can just find what the densities and temperatures in the flow are, and if photons are dominating the dynamics, at least I can do that. Sorry, you also include viscosity. Oh, in this context? Okay. Let's leave viscosity aside for now. I mean, photons can also impart viscosity. Let me not go there at the moment. So let me just assume we have an accretion rate, okay? And I'm going to model it. It looks like a disk expression where h is the half thickness of the disk. But let's just. I'm not even going to pretend that I understand where h comes from. I'm not going to invoke hydrostatic equilibrium. I'm not even going to invoke inflow equilibrium. Just at some radius, there's this m dot that's going through that radius, and it's going through a thickness h, whatever that h is. I'm going to specify the inflow velocity through a Shapiro-Sinyaev alpha prescription. That's merely a definition of alpha, just so I know how that factors into the results here. Nothing more than that. And then I get a density of 2 times 10 to the minus 13 grams per cubic centimeter, depending on radius and all of that. If I then make the extra assumption that radiation is transported through diffusion, through that thickness with some, and it's releasing accretion power, then I get a temperature of several times 10 to the 5 Kelvin. Thank you. Okay, and that immediately tells me that my radiation to gas pressure ratio is 10 million. Okay, so photons are important here. And this is, Jim is going to no doubt talk about this a lot in his talk. But turbulence, so we're in a different regime again from all the previous days in this conference. We are talking about radiation pressure dominated turbulence, and that's a whole other ball of wax, and I'm going to show you some of the complexities that can arise there, but I'm sure Jim is going to talk a lot more about that. Okay, when you're in this regime, it's actually, and this has been known for years, many, many years, you're actually in the regime of an envelope of a massive star. So think O stars, if you like. So this is the Roslin mean opacity. So that's the thing that governs both diffusion and exchange under optically thick conditions. This is temperature, and these curves are for various densities. And I just showed you that my nominal density is around 10 to the minus 13. So we're down here, and it's basically Thomson all the way except for this little bump here. This is infamously known as the iron opacity bump because it's due to all sorts of complicated transitions of iron atoms and ions here. In fact, I don't actually know what it's microscopically due to, but the opacity tables contain this feature. And you're missing the order of magnitude increase in opacity that would result from helium recombination and ultimately hydrogen recombination when you go with that, because you're just not dense enough. Okay, so under these conditions, the opacity is incredibly simple. So the physics should be very simple. It's just this little bump that enhances the opacity by 2, 3 at most. And I'm going to show you that that alone causes enormous changes. So this was perhaps first demonstrated again in massive stars by Yan-Pe Zhang and collaborators, including 2 people here. This is a 1D model of a massive star envelope. There's the iron opacity region. How do I know that? Because these are radiation pressure dominated structures, so hydrostatic equilibrium is having to face a constant flux that's emerging from the core. The acceleration due to that radiation pressure flux is kappa F over C. The flux is constant. So there, the opacity is, Thomson, but here you suddenly get an increase in that acceleration because of the enhancement of kappa. That's it. And that has to be compensated with something if you're going to be in hydrostatic equilibrium. And so what does the fluid do? It introduces a gas pressure gradient downward by creating a density inversion, which is obviously unstable. Rayleigh-Taylor, if nothing else, but it's also convectively unstable. The entropy is decreasing outward through that region. And when you simulate it, that's what you get. You get convection. But this is under the regime of slow photon diffusion. AGN are over here in the region of low density, very rapid photon diffusion. And in that case, you end up with transonic convection, supersonic convection even, with huge density fluctuations that result. So this is compressive turbulence, big time. Lots of porosity here through which photons can diffuse. And actually, when you take the time average, you still maintain the density inversion, interestingly enough. That's going to be important in what I'm about to show you, which is what happens when you put this in an AGN. Okay, so these are simulations of disks around AGN, which include these opal opacities. And I'm showing you snapshots of density, an azimuthal slice of density as a function of height and radius at different epochs. This is a highly time variable situation, and the variability arises for incredibly interesting reasons. But the thing that I want to draw your attention to is that you can see that if you go off the disk midplane, there are density inversions all over the place. And these drive supersonic convection in the disk. That convection itself is for some reason driving clumping, transient clumping of the disk in various places. These clumps form, they're actually rings, and then they dissolve, they form and dissolve. And you can see that more clearly in this plot, which shows a space-time diagram, radius versus time of surface mass density. And you can see this clumping up of surface mass density that then dissolves, clumps again, dissolves, clumps again. And you can also see that that's highly correlated with the presence of the iron opacity. Okay, all those red regions are where that iron opacity bump is kicking in. The reason for this has to do with the MRI stresses themselves, which are being enhanced when convection is occurring. And this is a phenomena that's been seen in a variety of contexts since at least 2014. And again, I think it's appropriate to mention this in a turbulence workshop. So this is a rather complicated plot for this simulation of various fluctuations as a function of time at 50 gravitational radii, which is, if I go back, about just outside here, okay? And what you're seeing, first of all, so let me draw your attention to two curves. The blue curve is the opacity itself, and you can see the opacity is going up and down, up and down. And remember, the opacity in this case only cares about temperature. So we're just above the iron opacity bump. When the temperature is high, you're at electron scattering. When the temperature is low, the opacity is enhanced. And how do I know that? Because the radiation pressure, which is a third AT to the fourth, it's a measure only of temperature. When the radiation pressure is high, the temperature is high, the opacity is low. When the radiation pressure is low, the opacity is high. So we're just oscillating back and forth on the hot side of the iron opacity bump. When you have high opacity, you trigger convection because you get these density inversions. That launches a whole bunch of turbulent kinetic energy in the green. It also enhances the magnetic pressure and indeed the magnetic stresses. For reasons which are still argued about, my point of view is very naive. You have vertical convection, which is creating colloidal magnetic field, vertical magnetic field, that enhances the MRI. That's nonlinear interactions being viewed through linear instability theory. You should not trust that at all. But anyway, you do get an enhancement of these magnetic stresses. That enhances heating, so the radiation pressure starts to climb, the opacity starts to drop, you lose the convection, you lose the enhanced stresses and everything, and so you start cooling, and then the opacity starts to increase again, and the cycle repeats and repeats and repeats. And these transient convective MRI cycles have been seen now in a whole variety of circumstances. This is the first time it's been seen in a global simulation where radiation pressure turns out to be important. All of the other simulations have been gas pressure dominated, which are much easier to understand. Okay, so it's these radial gradients and transient stresses that are causing this clumping. It produces variability on month timescales, substantial variability, so that's an attractive mechanism for explaining timescales in AGN. You don't need inflow time variations, it's thermal time variations, which work. Okay. How am I doing on time? Because normally, 5 minutes left. Okay, so I do need to go at lightning speed. Okay. Oh no, I have more time than that. Yeah. Normally I practice a talk, and then when I'm actually giving it, I go at twice the speed, so let me slow down because I'm probably losing all of you. I'm returned back to this opacity diagram because there's an interesting effect that has been seen in the simulations of massive star envelopes, and that's that can you actually get these opacities to enhance? So remember, all that I was due to this trivial little bump here, but if you can just produce orders of magnitude increases in opacities, just imagine what you might do. And the way you can do that is, remember, this turbulent convection is highly supersonic. It causes lots of clumping. This is a highly density dependent opacity, and so in those clumps you can drive up the opacity. And then the radiation pressure force is going to be that much larger, and you can actually cause huge outflows. And this has been demonstrated in massive star simulations. We would like to sort of do that here, or we're wondering whether that might play a role in AGN as well. So I'm now going to show you unpublished work, and it's very, it's preliminary in terms of our analysis, and even in the way I'm presenting it. So forgive me, this movie is way too baroque. It's got way too much information here, so I'm going to run it, but I want you to focus on density up here, opacity over here, and maybe the plasma beta over here, and ignore everything else. So if I play this. Okay, so naturally MRI is triggered. You get, actually right now the accretion rate is of order 10 Eddington. You'll notice that, actually let me pause this. You'll notice that I'm stopping or Jan Fei, who actually run the simulations, I don't pretend to do that myself. We're stopping the simulations at 100 gravitational radii, so we're quite far from the black hole here, and it's because I'm not interested in the stuff that's going on in the inner regions. I want to understand how this physics works. And so I don't want to track that with, short time steps. So let me resume this. But yeah, I had to mention that. Okay, so right now we're at high accretion. We're hugely radiation pressure dominated. The plasma beta is very high within the body of the disk. These black lines show you the photosphere. There's iron opacity in spades here. There is variability, but starting about now, you're starting to see density inversions, and those are reflected by enhancements in opacity there. Those density inversions are causing turbulent convection, just as we saw in the previous simulation. But you'll also notice that the plasma beta is now getting to be less than unity here. So it's becoming magnetically dominated. Out here in these regions, you still have turbulent convection. There are the density inversions. They're quite clear. They are maintained in the spatial average. And it's driving a whole bunch of variability. But we are clearly getting a magnetically dominated region as the accretion rate slowly settles down to be an approximate inflow equilibrium at about Eddington if we were to allow this, this accretion disk to go all the way to the black hole. By the way, I should, again, emphasize these are full radiation MHD simulations. There are photons here. They are leaving the disk. And that's right. No, sorry, yes, beta in the thermal pressure, it's radiation pressure over, it's essentially radiation pressure over magnetic pressure because gas pressure is negligible. Yes. Oh, this is 3D. Are you kidding? MRI turbulence? You can't do this in 2D. These are expensive simulations as a result, but make sure. How long have I been in this field? Okay, let me quickly go through this. Density mass, which is shows you where convection is going to be occurring through these various 4 epochs. You don't care about the simulation units. There are the density inversions that are triggering opacity-driven convection, where betas are about a unity actually here. And you can see that they're unstable because the entropy is decreasing outwards towards the density inversion from the midplane. These are the various forms of pressure. So radiation pressure up here, gas pressure is utterly negligible, magnetic pressure, and turbulent kinetic energy density. And you will notice in the regions where I have this opacity-driven convection, I have whopping turbulent kinetic energy. That is what's supporting the disk against the tidal field of the black hole. It's not magnetic pressure, not radiation pressure. It is turbulent kinetic energy that's being driven by this convection. It's supersonic, superalphanic turbulence. In the magnetically dominated regions, so where beta is less than unity, you can see that magnetic pressure and turbulent kinetic energy are an approximate equipartition. Oh boy, okay. Just quickly then, these are the various forms of turbulent kinetic energy. This is vertical, radial, azimuthal, and you'll see that it's entirely vertical kinetic energy that's actually producing the extra pressure support. Okay, so again, that's because we have convection here. Very quickly for Elliott, although I realized this morning that I don't quite have the exact plot because I misread something here. So this is the convective, the vertical profiles through a convective epoch, a convective region of the disk. And again, turbulent kinetic energy is the dominant form of pressure support. It is what's supporting the disk against gravity. And there's the entropy gradient, which again indicates that it's convectively unstable. In a magnetically dominated radius, magnetic pressure and turbulent kinetic energy are an approximate equipartition. I forgot to look at that log scale. So this is the interchange criterion. This is the undulatory criterion, ignoring the entropy stratification, which is very stable. But even though This is a slight gradient. That scale makes me realize I actually have to do the full Parker criterion. So yeah, it might be Parker unstable. We need to understand how this magnetically dominated thing is maintained. We have a very magnetically dominated simulation as well, which we're analyzing. Just quickly, it just happened. There are various proposals in the literature about how this saturates. The one by Biegelman and Armitage, I'll just say this, is looking pretty good. Okay, just 5 seconds. It's a balance between shear generation of magnetic field and magnetic buoyancy. And so it's saying that the Alfvén speed is the geometric mean of the vertical Alfvén speed and the Kepler speed, and it actually more or less works, I think. There's my summary, and I will stop.
Thanks, Omer. I have a question about the supersonic convection.
Yeah.
So you're getting convection to drive motions that have speeds much larger than the radiation sound speed? Because that's not so straightforward. Are you sure it's convection?
I am, well, am I sure it's convection? I'm sure that those velocities are present. I'm sure that there's a density inversion. I'm sure that there's a convectively unstable vertical entropy gradient. And
it's a couple supersonic, or it's how? I'm just thinking.
Oh, it's not hugely supersonic, but it is supersonic and superalphanic. But it is in excess, yes. Yeah, and sorry, this was also seen in the previous iron opacity simulations, and I need to check this, but I need to go back to Will Schultz's analysis of the massive star simulations, because I think that was also...
Yeah, I just wasn't sure how supersonic.
Yeah, but in an accretion disk where you have an extra source of power, yeah, it's being driven up that and it must be hugely dissipative, right?
Yeah, so since this is a turbulence conference, I have a question. So you have effectively a Prandtl number, a Peclet number, a thermal conductivity. I only have Peclet number in my head because Drummond reminded me what it is yesterday. So you have a thermal conductivity, but you don't have the photon viscosity. So do you think that would?
What do you mean I don't have the photon viscosity?
Oh, sorry, these are not. These are
full Boltzmann transport.
Good.
This is
non-phase
code.
So you have everything.
I have everything.
Okay, so then you must know actually what is your
if I only knew what a Peclet number was. I suspect that conduction is much more important than viscosity in this case. Yeah.
Omer, you said that the stress is enhanced by convection.
Yes.
That is not exactly trivial, of course. I believe you're right, and I also confirmed that in some cases, but this was exactly the argument in those years why MRI must be the mechanism and not convection.
Sorry, I should be careful about this statement. Sorry. Your question actually has two aspects to it. One is, first of all, this is vertical convection, not the sort of convection that was associated with ADAFs in the distant past.
Okay, yeah,
that's a different debate.
But I don't think that was meant. It was vertical convection.
This is vertical convection.
Yes,
that's
and also
right.
the argument of Balbus and Hollis in those years.
Yeah, and it's not the convection itself that's doing the angular momentum transport. It's still mostly Maxwell stresses. So no, it is the magnetic field that's doing it. But those Maxwell stresses are enhanced at least relative to the pressure. I shouldn't say that the stresses themselves are enhanced. Alpha is enhanced.
Okay, great. Yeah, thanks.
Omer, great talk. Thanks. I have a question regarding the magnetically dominated regime, because you say that it may sustain this Alfvénic turbulent kinetic regime long enough, but
yeah, right.
How long does it? But on the other hand, you need this continuous triggering of the opacity-driven outflow. Isn't that so? I'm interested in the time scales. How long?
Okay, so there are multiple, again, aspects to that question.
Sorry.
One, no, please don't be sorry. We're supposed to be having a productive discussion, and I'm glad that you're engaged. All of you are engaged. I was not expecting this. I was expecting that this was going to fall like a, lead balloon. Who cares about this? Let's get back to plasma kinetics. And I have enjoyed that, by the way. That was not meant to be. So there are two things. In the magnetically dominated regime, it's not convective, actually. Okay.
Right.
Although in the convective regions, it's beta Borda unity, so it's not, it's, you know, it's not dominated. But
yes, this is my point. So
yeah.
Can you?
Yeah, tease that out a bit. In the magnetically dominated regime where beta is truly low, we still have turbulent kinetic energy, which is roughly an equipartition with the magnetic energy density. I think that's sort of what you might expect. And it's all in radial azimuthal motions. It's not vertical. So again, there's no convection there. There was another aspect to your question. Oh, timescales. I wanted to say, and I'll say this and be recorded. All of the simulations that we've done in these flows do not run for a very, very, very long time. I cannot claim that we've reached any sort of steady state equilibrium structure here at all.
Right.
It may all be very much tied to the initial conditions, especially the magnetic field topology that we started off with. And
Right.
So buyer beware. Yeah.
So related to this, I didn't quite catch whether you said that it's kind of cycling between turbulent and magnetic domination, or at a given location, or is it some locations and other locations? Maybe you could just clarify.
Thank you, Eve. Yeah, I wasn't clear. So in the older simulation, it never became magnetically dominated. So it was literally cycling between thermal convection and then no convection, just diffusion. Back and forth, back and forth, back and forth. Here, what seems to be happening, and we moved a bit further out because, again, we were trying to tickle the dragon to get to lower temperatures. Here, what happens is those cycles of convection, which still don't alternate between magnetically dominated, or it's just convection being present or not. But that region where convection is occurring is moving out as the accretion rate is getting lower and sort of to establish an inflow equilibrium. And it's becoming magnetically dominated in the inner regions, which are pushing out the convective regions. So it's not alternating between convection and magnetic domination in time.
You say you want to talk about, say a few words on whether they are driven by heating or it's maybe magnetically driven, more like...
I would love to know. I mean, I think okay, so I subscribe to the point of view, maybe it's because Shane Davis was my former grad student, that it's a natural way of explaining the 1,000 angstrom break. And if you associate winds with that it has to be somehow associated with that break, and it's at 1,000 angstroms, and every time you see a fixed wavelength, you know it has to do with atomic physics. I think these are line-driven winds. It has to. This might enhance line-driven winds to happen, but no, I think it's line driving.
And in the simulations?
In the simulations, we have not succeeded in getting those outflows, and we don't have line, CAK force multipliers or anything. I'm sorry?
But you have magnetic outflows.
There is outflowing gas, at altitude. That's true. Yes, not significant in terms of the accretion rate.
Well, Chris sets his thing up.
So just one thing. Sorry to be a bit tongue-in-cheek. Given the last statement you had there about Shakura-Tsuniaev disks, would you say then it's fair to say that Shakura-Tsuniaev, sorry, I can't say this right, disks are sort of the accretion disk equivalent of the slab plus 2D model for turbulence? Archaic and relegated to the traction of history?
Fortunately for me, given that this is being recorded, I'm not familiar with the slab plus 2D model, so I can be agnostic about it. Okay.
Okay, Elliot says yes. It is canon.
I'll ask my last real quick question. Since you're running 3D simulations, do you have enough resolution to resolve some of these clumps? And do you see the universal clump mass distribution that your colleague Pengel has been talking about?
I do not know. We have not looked at the mass distribution of clumps, and the only thing I know that we're well resolved in is in terms of the MRI. We have not looked at that.
You should.
Is this a multi-phase?